Today I'm going to talk about one of my PhD projects called Spaghetti. It's for a streaming accelerator for sparse matrix multiplication. It specifically targets highly sparse matrices, and we evaluated the results and the architecture on FPGAs. So that's why you see the FPGAs title on the FPGAs on the title. The work was published in HPCA 2021, and in that time I was a researcher, as Dr. Najafi said, at Simon Fraser University, and I was a PhD student at the University of Tehran. All right. So I will talk about sparse tensor algebra and sparsity pattern, and then I will talk about the state-of-the-art sparse GEMM accelerators. Then we take a look at the GEMM algorithms, in particular inner product versus outer product algorithms. And then we show the spaghetti framework and architecture, and then evaluations. All right, and please feel free to interrupt me if you have any questions. All right, sparse tensor algebra. We use linear tensor algebra these days almost everywhere, from machine learning algorithms to graph processing, recommendation systems, simulations, computational biology. So most of these algorithms work with tensorized kernels, either matrix multiplication, matrix vector multiplication, convolutions. But in particular, GEMM or GEMM-V, matrix, and matrix vector are maybe the most commonly used tensorized kernels in these algorithms. And the challenge is that these matrices that we work with are usually sparse, and they are usually super large, and the level of sparsity can vary from low sparse to high sparse matrices. And today I'm going to talk about specifically, I'm going to talk about highly sparse algorithms. So when the matrices are super large, because our on-chip memory is limited, we're going to have some problems. And when the tensors are highly sparse, the operation intensity will be lower than what we expect, and we cannot utilize the memory bandwidth efficiently. As you can see, the density of the matrices varies from application to application. In deep learning algorithms, we usually have matrices that are 50% to 1% dense, but we have different algorithms, different applications, like recommender systems, graph processing, where the matrices are highly sparse. This is like the dimension of a graph from Twitter, and the density, and as you can see, we have more than 40 million elements, but the density is very low, almost close to zero, but it's not zero. So the thing is that the pattern of the sparsity, or the distribution of the non-zero elements, impacts on overall performance and throughput of our GEMM algorithms. As I mentioned, problem domains are sparse. The level of sparsity could vary from an application to another application, and it is hard to capture data reuse and parallelism. If you have just two dense matrices, you can easily parallelize the matrix multiplication. It's just a nested loop, so you can just unroll these loops and do some tiling and parallelize it and reuse data as much as possible. But in case of sparse matrices, it's really hard to pipeline and parallelize the whole algorithm because you're accessing to zero elements and non-zero elements. All right, so let's take a look at dense GEMM, general matrix multiplication on systolic arrays. Systolic arrays are one of the most popular architectures for matrix multiplication. So we usually have a 2D grid of processing elements, and each processing element has a multiplier and an adder. In this picture, I have like 128 by 128 grid, like a mesh of processing elements. And we can take a tile from the left matrix A and another tile from the right matrix. In this example, the right matrix, we keep it stationary in the processing elements, and we like send the left matrix into the processing element in a streaming fashion, from, in this case, from left to the right. And then we do the reduce operation in another dimension. So we send like the left matrix from left to right, and then we do the reduce operation from top to the bottom. We reduce the partial sums. So it offers like a high data reuse, and like the architecture is very scalable. You can easily scale it up or down based on the limitations that you have in your hardware. But there are some challenges with systolic arrays. In particular, when the matrices are either irregular or sparse, the systolic array cannot offer a good performance. On the left, I'm showing an irregular matrix multiplication. We can still take the first tile from the right matrix and put it in the processing elements. In this case, I have 128 by 128 systolic array, but the height of my tile is only 32, so it occupies the first 32 rows of the systolic array. But I cannot take the next tile, because if I put the next tile in my systolic array, then the result will be incorrect. I cannot do the reduce at the same time. So that means that I have to do the first tile. Then once it's done, then I can start doing the multiplication of the next tile. And this problem gets worse if the matrices and these tiles from A and B are sparse, because then we will have 0 operands in our processing elements. So we're gonna see underutilization in our systolic array. Now let's take a quick look at the algorithm, the inner product algorithm. So what is the problem with the inner product when the matrices are sparse? Let's say that we have 2 matrices of size 4 by 4. We usually store the matrices in a compressed format, because we don't want to store zeros, right? We just want to store non-zero elements. So we usually use a compression format or a compression representation, like CSE or CSR. These are probably most popular compression formats: compressed sparse row and compressed sparse column. So for this matrix A, we store only non-zero elements. This val array is an array of the non-zero elements that we have in matrix A in a row-wise order. And we need another array that indicates the column index corresponding to every non-zero element that we have. For instance, this yellow one, the column index is 1. The next one, the column index is 3. And we have a pointer array. And the pointer array is like a differential array where the difference between every 2 consecutive element shows the number of non-zeros that we have in that particular row. For instance, here in this case, 2 minus 0 equals 2. That means that we have 2 non-zeros in row 1. Then 5 minus 2 is 3, so we have 3 non-zeros in the next row. CSC is the same thing, but in a column-wise order. So if you want to do a matrix multiplication using inner product approach, you need to take one row from matrix A and one column from matrix B, and then you do a dot product and then reduce the partial sums, and that gives you the first element of the final output matrix. But the thing is that in this case, you are reading only the non-zero values from memory. So that means that you have to check the indices, and you have to see if the indices match, then you can do the multiplication. If not, you just need to skip that multiplication, right? For instance, the first element that I read from matrix A is this yellow one, and the first element that I read from matrix B is this green one, but I cannot do the multiplication because they are located in different locations in this row and in this column. So if you look at the code, before doing the multiplication, I have to do this index matching, and this is probably the most challenging part of inner product sparse matrix multiplication. And the state-of-the-art accelerators are trying to optimize and find a better solution for this index matching. One of the papers that was published in HPCA 2020, it was actually the best paper in HPCA 2020, called Sigma. They proposed a flexible systolic array. So as I mentioned, inner product requires index matching. So they proposed a flexible interconnection network. So processing elements are still arranged as a 2D grid, but the connection between the processing elements is like a more flexible connection. So you can, in case if you have any mismatch in indices, you can select different weights or different activations from different locations. But the thing is that this interconnection network is expensive and it requires a different storage format. So I don't want to go into details, but it is worthwhile taking a look at this paper. It's a decent paper, but they use bitmap instead of CSR or CSC, and the thing is that we usually work with CSR CSC. So most of the highly sparse matrices are stored in CSR CSC format. I will talk about that in a minute. And so in this case, we have to convert everything to bitmap, and then we have to convert the output matrix back to CSR CSC before writing back the result into the memory. But what is the problem with bitmap? As I mentioned, compressed sparse row CSR or CSC, we have a pointer for non-zero elements. Let's say that the n and z is the number of non-zero elements. So we have a pointer of size n and z, and an index array again of size n and z, and a pointer array of size n plus 1. But on the other side, in bitmap, we have for a 5x5 sparse matrix, we need to store a 5x5 matrix as a bitmap representation, and each element is just one single bit that indicates whether the corresponding element is a 0 element or a non-zero element. So no matter what the size of the matrix is, you need to have n by n bits stored in the memory to represent the sparsity pattern of the matrix. So if you look at here, I'm showing the number of DRAM accesses, or the number of bits that we need to store in DRAM for a given, I think, 10,000 by 10,000 matrix, but different levels of sparsity or density. And as you can see, when the matrix is relatively dense, bitmap is a better option compared to CSR or CSC. But when the matrices are sparse, like the density is below like 3%, 2%, then CSR, CSC would be significantly better, orders of magnitude better compared to bitmap. Why? Because bitmap would still need to store n by n bits, while only a few elements are non-zero. You have to still store n by n bits in the memory. But in CSR, CSC, you only store the non-zero elements and the corresponding metadata, or like the index, like column index or row index of the corresponding non-zero elements. So for highly sparse matrices, bitmap is not a good option, and it's better to use either CSR, CSC, or some representation formats similar to CSR, CSC.
Hey, sir, is it
Yep.
possible that we can have some sort of or some published papers that keeps a measure of the sparsity, and then we will have some sort of look ahead? Does that point is clear? Like, yeah.
Mm-hmm.
Okay.
Yeah, well, that's a good point. It depends. It depends on the overhead of this, like converting from one format to another format. Sometimes you need to parse through the metrics ahead of time, and that takes time, right? But yeah, we can convert based on the level of sparsity, and that is probably like the smartest thing to do, but it depends. It depends on the overhead.
Okay.
Yeah. All right, GEMM algorithms. Now let's take a look at the inner product versus outer product. So in the inner product matrix multiplication, we take one row, one column, and we do a dot product operation, and then that gives us the first element of the output matrix. But we have another protocol. We have another algorithm for matrix multiplication called outer product. It's pretty simple and kind of similar to inner product, but in a different order of operations. So in outer product, we take one column. We take one column from the left matrix and one row from the right matrix, and we do an outer product instead of a dot product. And the output of the outer product between two vectors is a matrix. So this outer product gives us a matrix. We call it a partial matrix. So we have three pairs of columns and rows, and like every pair gives us a partial matrix. When we reduce and accumulate these three partial matrices together, we get the final output matrix. So we have a multiplication phase, like outer products between like the pairs of columns and rows, and then we have this like merge or accumulation phase that accumulates the partial matrices. Here I'm showing a 2x2 example just to show you that the result would be completely the same, and we have the same number of multiplications and additions. So there's no difference in terms of the number of operations that we're doing. But what the benefit of the outer product is the index matching. Let's say we have two matrices, and these are like sparse tensors, and we have stored them in using a compression representation system like a CSR, CSC, and CSR. So I have to take one column from matrix A and one row from matrix B and do an outer product operation, and that gives us this partial matrix 0. And the point is that the outer product doesn't need any index matching, because every non-zero element that we have in this column should be multiplied by every non-zero element that we have in this row. So in this case, we have two non-zeros here, one non-zero in this row. That gives us this partial matrix with this format. If we if you look at the coordinates, we will have two non-zeros, and the column index is coming from the column index of the non-zeros in this row, and the row index is coming from the row indices of the non-zero elements in this column, right? So 1, 3, so 1, 0, and 3, 0, 1, 0, and 3, 0. If we do the same thing for like the rest of the columns and rows, pairs of column and rows, we will get 4 partial matrices, right? Because we have 4 columns, 4 rows. And when we merge these 4 partial matrices together, we'll get the final matrix. So the benefit of Euler product is that we don't need to do index matching anymore. But the problem is that these matrices that I'm showing on the bottom of this page, these are like the actual values that you get in real hardware. So you don't see this in hardware, because this is just the representation of the matrix. You see only the non-zero elements, right? And in order to do this accumulation or merging phase, you have to sort the non-zero elements, because you need to find the non-zero elements with the same coordinates. For instance, here in P0 and P2, we have this like 1, 0 non-zero element here, and 1, 0 like this orange one here. So these two elements are in the same location. So in the accumulation phase, I have to accumulate those, I have to reduce those two, right? And that gives me this one. So in order to do that, I have to, well, I have these 4 arrays of non-zeros after like doing the multiplication phase. Now I have to sort them and then find the non-zeros with the same coordinates, and then I have to merge them, and that is my result. And doing this sorting is expensive in hardware. Like sorting is like you know, is a costly operation in any hardware. But the benefit of Euler product is still that we don't need this index matching. There were a couple of papers published that are using the Euler product approach, and they are targeting this issue with Euler product, like the merge phase. For instance, this paper, Spark, again published in HPCA 2020, their idea was that we can, if you look at these two matrices, A and B, 5 by 5, when we do the multiplication phase, we will get 5 partial matrices, right? Because we have 5 pairs of columns and rows. What we can do is that we can condense the left matrix. We can condense matrix A to the left, and then we can do the multiplication. So in that case, we will have only 3 partial matrices, because we have only 3 columns in matrix A. So this idea reduces the number of partial matrices, and that means that it reduces the cost of doing this like merging and sorting every time. But the problem is that you know, let's say if I have only 2 multipliers, when I condense it to the left, the number of rounds of doing like the whole operation still depends on the longest row. Let's say I have a sparse matrix, but it has only 1 row which is fully dense. So in that case, I cannot decrease the number of, you know, like rounds of operations. And the thing is that like maybe the most important challenge with this approach is that when you condense the left like the matrix A or the left matrix to the left, now you will have like non-contiguous memory accesses, because now you need to read the values in a different format, and you have to fetch the corresponding rows from matrix B again in a different format. In a regular outer product, you take column 0, you need row 0 of matrix B, right? Then you take column 1, you need row 1. But in this case, you take column 0, but in column 0, you need row 0, row 1, row 4. So you need different rows of matrix B. So you're accessing to different locations, like non-contiguous locations of matrix B in the memory. So that means that you cannot have a fully streaming architecture, and that it needs a prefetcher, or it needs a cache, and that is expensive. But the idea is a great idea, probably for the accelerators that can afford having a cache or a prefetcher. So we talked about inner product and outer product. We talked about two state-of-the-art accelerators. So inner product requires index matching and probably a different storage format, and the input data reuse is not good, but the architecture is scalable. On the other side, the outer product doesn't need index matching, probably a better storage format, but still it's not scalable. And the parallelism, because of this merging, is not good. So we are looking for an architecture that can offer like better data reuse and parallelism, and it is also scalable. So our key idea was to do this outer product, but in an output parallel fashion. Let's look at this example. Let's say I have, again, two matrices, 4 by 4. They're both sparse. For just sake of simplicity, I have two multipliers in my like hardware. I can afford having only two multipliers. So in that case, I need to split the pairs of columns and rows into two groups, right? Because I have two multipliers. So I send like the first two pairs of column and rows, column 0, 1, row 0, 1 to the first multiplier. And then this like the third and fourth columns and rows, 2 and 3, 2 and 3 to the second multiplier. So this is okay, because the multiplication phase in outer product is highly parallelizable. So you like for every pair of column and row, like every pair of column and row is independent from the others, right? You take one column, one row, then you take another column, another row. So they are completely independent. So you can do this multiplication phase in parallel, and that's like good compared to inner product. But what does the output look like? The first multiplier here is producing partial matrix 1 and 2. And the second multiplier is producing partial matrix 3 and 4. So now I have to merge and sort these two arrays of non-zero elements. Let's say I have only two sort and merge components in my hardware. I cannot afford more. So in that case, the idea is that if you look at these partial matrices, you can do the sorting and merging in every row individually. So like each row is kind of independent from the rest of the rows. So I can like merge and sort the first rows of partial matrices, and then I can merge, sort the second row, and then the third row. Well, there's no non-zero element in the third row in any of these partial matrices, and then fourth row. So the idea is that if I can put an allocator here and send the even rows to like the first sorter and merger, and the odd rows to the second one, I can do this sorting and merging kind of in parallel, right? So I can parallelize the sorting and merging. So rows are mutually independent. So the first one does the sorting and merging for row 0 and row 2. In row 2, I have no non-zero, so it produces only the non-zeros in row in the first row, row 0. And the second one does the same job, but for row 1 and row 3. And so if you look at this architecture, now we have like 2 sorters and mergers that are doing the job in parallel. And well, the load might be a little bit different. I mean, here, this one is producing only 3 rows. This one is producing 5, producing 3 elements. This one is producing 5 elements. But we can still do this in a like in parallel. So the key idea is this like row-wise sorting or row-wise splitting, and it's like it helps to improve the performance. So based on this idea, now we can propose the microarchitecture of our accelerators. Let's say we have like a bunch of multipliers, depending on the budget that, like the area or power budget in our chip, like either an ASIC or FPGA. And we have a bunch of sort merger components. I'll talk about the architecture of the sort mergers in a minute. And then we put an allocator in between, and the allocator is a modulo-based allocator. And then we can stream into the multipliers from DRAM, like the input values, and then the output goes back to DRAM again in a fully streaming fashion. It is scalable because you can play with the number of multipliers and number of sorters and mergers based on the budget that you have in your hardware. And the output is also parallel. The input is already parallel because of the outer product algorithm, but now the output is also parallelized. This is the architecture of the sorters and mergers. As I mentioned, sorting is an expensive operation in hardware. So we just wanted to have a fully streaming sort unit in our hardware. So this is a serial input, serial output sorter. But the question is that what should be the size of the sorters and mergers, and how can we tile like the big tensors, big matrices, and how can we split them into smaller pieces with this approach? Let me first talk about the sorter and merger architecture. So this is a 2-stage sorter, and we have an accumulator or a merger in the end. So this is kind of like a similar to binary sort, but it has been flattened out. So we have 2 stages here. That means that we can support an array of length up to 4, and within each stage we have a multiplexer with a comparator that selects the smaller value, and we have a demultiplexer with a counter that switches the demux output every 2 to the I cycle, and the I is like the stage number. So it is a pretty simple sorter component. So like every clock cycle, we take in like a value from the input, and it is like fully streaming. So if I like show you the cycles after 10 cycles from 0 to 9, we will have the result sorted on the output side. So the stages is like the number of stages is 2 log n. That means that we can sort an array of size 4, and the cycles is 2 times n plus s. Now with this sort merger, here I am showing like the architecture of spaghetti in more details. So we have multipliers, And we have a bunch of like FIFOs prior to every multiplier. So we can stream into these FIFOs like the values of A and B, like the columns and index in the indices. And then we have this modulo-based allocator that like calculates the row index modulo depending on the number of sort mergers that we have. If we have only 2 sort mergers, that means that we are like splitting them like into row numbered values and odd number values. And just for like remove, like, you know, sometimes you might have 2 values coming from 2 multipliers that are both for this, like the same sorter and merger. Let's say they are both like an even from an even row. That means that you're going to be like a blocking issue here, because they both have to be sent to the same sorter and merger. That's why we added these queues or FIFOs called virtual channels, just to alleviate this head of line blocking issue. This is kind of like similar to what we have in network on chips. So these are like the virtual channels, and we have sorters and mergers. And the thing is that I showed you the structure of the sorter and merger. So you can have, based on the like the budget that we have in our hardware, you can have either deeper sorter and mergers, or you can have smaller sorter and mergers, but you can increase the number of sorter and merger components that you have. So instead of having only 2, you can have 4, but sorter, but smaller sorters. But the question is that what is the size of the sorters and mergers? In this slide, we saw that, for instance, if we have a sort unit of size 2, like 2 stages, we cannot sort arrays bigger than size 4. So we need to be careful about the arrays, like the values that we are sending to every sorter and merger, right? They cannot exceed the depth of the sorters and mergers that we have in our accelerator. And like we have to tile the matrices in a way that they, like, the size of the arrays won't exceed this the depth. So this is like the second part of our framework we called pattern-aware tiling. As I said, the on-chip budget is limited. Let's say we have 2 multipliers and 2 sorters, and the depth of the sorter is ds, and in this case, let's say is 4. And I have 2 matrices, 5 by 5. So I need to make sure that when I send the non-zero elements, they won't exceed the depth of this sorter, right? So if you look at these 2 matrices, if I do the first outer product, like first column and first row, this would be the partial matrix. And the second one, this is the second partial matrix that I will get. The way that we can do this is that we can like compute the number of non-zeros that we are producing in every partial matrix. For instance, here in P0, like partial matrix 0, we have 1 non-zero in row 0 and 1 non-zero in row 3. In partial matrix 1, P1, we have 2 non-zeros in row 1. If we do like the same thing for the other 3 partial matrices, then we will have this table. Then we can this column shows the sum of the non-zero elements in every row along these 5 partial matrices. For instance, the R0 is going to have 4 non-zero elements, one from P0, another one from P2, another one from P4. Like R1 is going to have, again, 4 partial matrices. That means that if you look at the depth of the sort mergers, the depth is 4. R0 is an even row. R1 is an odd row. That means that if I send R0, that will occupy my sort merger, and I cannot send any more even numbered row to the sort mergers. If I send the R1 to the second sorter, the size is 4. That means that I cannot send the next odd row, which is R3, to this one, right? So I have to stop there, wait until the compute is like this round is done, then I can start the next round. So that is how we do the tiling. So, you know, for doing this multiplication, we can tile matrix A. We can split it into 2 horizontal tiles. The first tile has only 2 rows, R0 and R1. And then the next tile has the rest of the rows, R2, R3, R4. So we can easily split this multiplication into 2 rounds. The first round is doing like the first 2 rows of A times like the entire matrix B. And then the second round is like the next 3 rows of A, again by entire matrix B. And in this case, we can make sure that when you do the first tile, the number of partial products that the multipliers are producing won't exceed the depth of the sorters and mergers, right? This is the algorithm. I don't want to go into details, but we need to basically see the locations of the non-zero elements in A and B ahead of time. Then we can decide how to tile the matrices, and then we can send them to the accelerator. All right, so once we do this horizontal tiling, now we know that the tiles are smaller than the size of the sorters and mergers. Now we can do like another step of tiling. We call it segmentation. So we have 2 multipliers. So we want to make sure that we are balancing the load between these 2 multipliers evenly, right? So let's say we have 2 multipliers. In the first round, I'm going to do the tile 1. So if you look at the tile 1, we're going to do outer product, right? So we're going to take columns from like tile 1 of matrix A and rows from matrix B. So if I divide it in this way, like the first 3 columns of this tile 1 and first 3 rows of matrix B, and then column 4 and 5 from tile 1, row 4 and 5. If you look at the number of multiplications, they are almost like they are, in this case, exactly the same. So we will have 4 multiplications for the first segment, like the first pair, like 3 pairs of columns and rows, and we have again 4 multiplications in the second segment. So again, this is like the algorithm. So we can determine how many columns to be sent to the first multiplier and how many like columns and rows, pairs of columns and rows to be sent to the second multiplier. And we can do this for every tile. So we can do the same thing in tile 2. Like in tile 2, the result would be not exactly the same, but almost the same. So it's going to be like a load balanced multiplication. So it minimizes the idle cycles in the multipliers, and we can utilize the input memory bandwidth more efficiently, and we can balance the load of the multipliers. Again, this is the algorithm. I don't want to go into details, but this is what we are doing. So we like in the first like I think in this slide I can show you a summary of like the tiling approaches. So we take 2 matrices, we do the tiling, horizontal tiling first, then we do the segmentation. In this case, for every tile, we need to do a CSR to CSC conversion, and that is like the drawback of this approach, but we have to do that. But the point is that we are doing this tiling in a pipeline fashion. So here on the bottom right of this slide, I'm showing like the the pipeline, or like the multiplication and merging phases of different tiles. So we have this scheduler on our host processor, right? So the scheduler starts doing scheduling and extracting the tiles. Once it extracts the size of the first tile, then it can let the accelerator start doing the multiplication of first tile, and then at the same time the scheduler starts doing extracting the tile, the second tile, like tile 2, right? So everything is in a pipeline. So we're not doing the tiling first. Once it's done, then we start doing the multiplication. No, it can be in parallel with actual multiplication in hardware. And the result would be a what we call a pattern-aware tiling, right? If we have this dense matrix, a loop tiling, like a regular loop tiling, means that you just tile the matrix based on the size, right? So on the right, you see the loop tiling where we have this tile completely 0, right? But the pattern-aware tiling means that every tile might have a different size, depending on the number of non-zeros that we have in every tile. All right, so with this architecture and the scheduler, we proposed spaghetti. So this is the architecture. We have an RTL generator written in Chisel. Chisel is a high-level hardware description language embedded in Scala. We have this pattern-aware scheduler. So Chisel generates the RTL based on the constraints and based on the design parameters that you give to the generators, like the number of multipliers, number of sorters, depth of the sorters, and then it generates the RTL. You can just deploy the RTL on an FPGA. We used Amazon F1 instances FPGA, and we use this pattern-aware scheduler on our host processor. This is just like a sample of our Chisel. It's very parameterized. You can play with the parameters that you have, number of multipliers, as I said, depth of the sorters and mergers, and the number of sorters and mergers that you have. So this is the flow of our GEMM, Sparse GEMM acceleration engine. So the host processor is connected to the FPGA through PCI Express, and they are both connected to DDR. The FPGA starts reading and fetching the input values from the DDR4 memory, and then it writes back the result to DDR. The evaluation, we took a bunch of sparse matrices from Sweet Sparse dataset. These are highly sparse matrices. If you see the n is the dimension, for instance, this one is 100,000 by 100,000. It's a super large matrix, but the number of non-zeros is very small, just 1.6 million in almost a billion size matrix, right? So the density is very low, and they are from different shapes. For instance, this one is more like a diagonal matrix. This one is more an irregular matrix. We just classified them into two shapes, diagonal and non-diagonal. And on the last column, you see the number of tiles given the the number of multipliers and sorters that we have. So we used Amazon F1 instances and Intel CPUs and GPUs. We ran the whole multiplication, and we were 5 times and 8 times on average better than CPUs and GPUs. Using this Chisel generator, we were able to do some sort of design space study based on the pattern of the matrix. As I said, just diagonal versus non-diagonal. We observed that, for instance, in F1 instances, for diagonal matrices, it's better to have more multipliers and less number of sorters and mergers, obviously deeper sorters and mergers. And in non-diagonal matrices, we have only 16 multipliers, but 32 sorters, but obviously smaller sorters. The number of VCs, we observe that 3 is a good option, and the depth of the VCs are 32. And as you can see, you can see a sweet spot for every parameter. So we can just sweep the parameters and see what the best optimal design is for every like every category of the tensors.
Dr. Reza, it seems like the graph that the lower left seems like, is that limited by Amdahl's law? You know, like you keep giving more and more.
This one.
What is the DVC axis? What is the DVC?
DVC is the depth of the virtual channels, those FIFOs that we had.
As that depth
behind
higher and higher, you're not getting any speed up, right?
Yeah, exactly. So more than 32, we're not getting any speed up.
I see.
Because it depends on like the number of, like the amount of contention that you have. If you have 2 values for the same sorter, then you need just a queue just to, remove this like blocking issue.
Not being parallelized. Is that the conclusion there when your depth is it's not being parallelized, right? You're limited by it's not being parallelized?
Yes, exactly. I mean, beyond a certain point, it won't help, right? We just need, a small FIFO, but 3 FIFOs, right? For like just for removing this head of line blocking issue. But like VCs are not that much helpful, as you can see. I mean, they help just a little bit, but the main parameters are number of multipliers and number of sorters and the depth of the sorters, because that impacts directly on the tiling. If you have deeper sorters, you will probably have bigger tiles, right? Yeah, so in summary, so we talked about inner product accelerators and outer product accelerators, and Spaghetti is better in terms of scalability, data reuse, and we propose a pattern-aware scheduler. In general, we observed that for highly sparse GEMM, outer product is a better approach compared to inner product. But for relatively dense GEMM, like what we have in deep learning, for instance, it's kind of it's debatable. I think inner product might be better a little bit. But if you have like highly sparse GEMM, we compared Spaghetti against Spark, the other state-of-the-art outer product accelerator, and we showed that Spaghetti was offering a better performance. But overall, my conclusion is that finding the best architecture for sparse tensor algebra depends on the level of sparsity and the pattern of sparsity. Here we assumed that our matrices were like highly sparse, and the non-zero elements were distributed randomly, like uniformly across the matrix. If you have a non-random matrix, if you know the pattern of like the non-zero distribution in your matrix, you might find a better solution, a better architecture, a better storage format, right? So everything depends on level of sparsity, and we cannot propose one solution, one architecture for like the whole design space, any tensor of any levels of sparsity. Yeah. So yeah, this is my conclusion that I just talked about. And the Spaghetti framework is, as I said, written in Chisel. It's open source. You can take a look at the code. And I believe that's my last slide. Yeah, and that this is the link to the code.